Hello, I'm Daniel Schmidt, and my mentors were Dr. Mike Tiagi and Dr. Michael Malisoff. Today we're going to be talking about computer simulation, mathematical model, and experimental analysis of severe slugging in a ride. Now, what is severe slug flow? According to the Schlumberger glossary, it's a multi-phase flow regime in pipes in which most of the lighter fluid is contained in large bubbles dispersed within and pushing along the heavier fluid. The word slug normally refers to the heavier, slower moving fluid, but sometimes to the bubbles of lighter fluid. So if you kind of shift your eyes over to the right, you'll see a diagram of a scenario in which slug flow can happen. You have a blockage of the riser base, a slug growth, and then a liquid production. That gas is going to break through. You get a fast liquid production, and then the gas production and the gas blowdown. So why do we care? Why do we care about severe slug flow? And who here likes Oreo cookies? Well, you should, because they're absolutely fantastic. And if you're like me, you're going to get the double stuffed Oreos, and you're going to pull them apart just like when you were a kid, and you're going to eat that cream-filled center first and then save those two chocolate crackers for later or eat them then. Well, in the oil industry, that cream-filled center, that Oreo, is analogous to our oil production. We love the oil production. It makes us a lot of money. We want to get more of that. That chocolate cracker part is going to be like our gas flow. Kind of like plays the part of like a tax return at the end of the year. You weren't banking on getting it, but I'll be dang, you're going to spend it. Am I right? So that's where that kind of falls into play in this scenario. And this is with respect to wells that were in search of oil and not the lucrative gas wells. So if you look at the diagram, you could probably easily see that you're going to get some oscillations during this flow regime, and you're going to get that slug growth. Maybe you have a pressure buildup down there at the bottom, and then maybe a pressure spike, and then a drop when that fast liquid production happens, and that hydrostatic head disappears. Well, first thing you need to ask yourself, what is pressure? Well, if we took everybody in this room, or I did, and we started compressing the walls, moving the walls in, first you're going to be really PO'd that I put you in this box and started compressing it on you, but you're also going to start feeling a force, right? And exerting a force on your neighbors and on the wall, and that what you're feeling is pressure. Now, what if I told you you had to move in a particular direction while you were undergoing this pressure, and let's say I was expanding and collapsing the box on you? Well, it's easy to imagine that when the box was expanded, you're going to move faster, and when I collapsed it more, you're going to move slower. You're going to start tripping over your neighbors, right? Well, what is the wall feeling in this scenario? Well, the wall, if you've ever been really bored at your office and you probably should have been working, but instead you reached over and grabbed a paper clip and started bending it into really cool, funny stuff, right? And you started bending it back and forth, back and forth, back and forth. And it's eventually going to snap. And why is that? It's no brainer, right? Fatigue. There's fatigue inside of that paper clip. Well, that wall is going to be feeling the same thing. So why do we care about severe slug flow? Well, we want as much cream-filled Oreo as we can get. So why? Because it's going to make us the most amount of money. We also like our penguins to have tuxedos, not to be covered in black wool. We don't want our pipes to break because environmental cleanup leads to money, right? We don't want to go there. Now, last and one of the most important reasons is we don't want to get anybody injured, killed. Why? It leads to money, right? I mean, you don't want to get anybody injured or killed anyway, but even if you're a cold-hearted businessman, that leads into money, and you just don't. So what is the mathematical model? It was developed by DiMeglio et al. It's for using with control in the slug flow process. And these and others like it are for that purpose. It consists of three differential equations. Here they are given to you there. X1 is going to be your mass of gas in the bubble. X2 is mass of gas in the riser divided by mass of liquid in the riser. And X3 is going to be mass of liquid in the riser. So if you look at the diagram over there on the right, the main principle of this mathematical model is you set a virtual valve down at the riser base, and it's positioned just at just past the bubble, and it's going to allow the gas to be pushed out, but it's not going to allow any reverse flow to come back through. And this proves vital because this is how it produces the slug flow. When that pressure in that bubble gets larger than the pressure at the riser base, it's going to let go a gas all at once, and then you have your corresponding. Now, what did we do for the simulation? CFD simulation was done with ANSYS Fluid. We used a similar geometry to the experimental setup as far as pipe diameter and distances go, but the input flow rate for gas and water were different, but keep in mind this is also a qualitative analysis, so the numbers obviously are not going to match up. Now, the mesh consisted of 17,056 nodes. A little background about ANSYS Fluent is that it solves for mass, momentum, balance, phase field, performed linear interpolation, and gathered the data. We used VOF, volume of fluid, and there's the equation given to you there, and then momentum, and there's the corresponding equation with it. What did it look like when we got? Well, there it is. So if you look at the riser portion, you can see you have the slug flow and the gas bubbles coming up. But if you take a look down there at the bottom on the horizontal portion, you can see a separation between the gas as it's moving along. And the red corresponds to all gas, and then the blue, pretty much a no-brainer, corresponds to all. So the experimental setup. We had a pressure sensor at the choke valve. There's the riser, a flow meter there. The air flow meter had a valve on it, so we could pretty much adjust the injection rate of gas to whatever we wanted there. And then pressure sensor at the base, air compressor, and water. It looked like this. You can see you have the Taylor bubbles coming up and then the trailing bubbles coming in behind it, and the oscillations of production there at the top. All those wires come into the box on the right, and it's hooked up to an Arduino Mega, which we using C++, interpreted the data from the sensors. So what is the data comparison? Well, if you look on the right between the experimental, CFD, and mathematical model, the flow rate and the velocity and liquid all has those nice mountains or peaks going on, right? Then if you look over at the pressure and massive liquid side, you can see sort of a buildup and drop off on the pressure side. So lastly, I want to give a special thanks to everybody that's helped. Been absolutely fantastic. And especially want to thank the CCT and NSF for this experience. It's been a whole lot of fun. Dr. Richard Hughes and Campanile Charities for the model funding. And at this time, I'd love to take any questions. Thanks.